From the dawn of humanity, we have gazed at the stars. We have pondered our place in the cosmos, and we have dreamt of traveling through time. The allure of time travel, the ability to witness past glories or future wonders, has captivated our imaginations for centuries. Stories of time travel from ancient myths to modern science fiction reflect our deep-seated desire to break free from the constraints of time. Imagine witnessing the pyramids being built. Picture traveling to distant galaxies. Time travel, if possible, would redefine our understanding of reality. The concept of time travel is more than just a fantastical idea. It is a question that has puzzled scientists and philosophers for generations. Can we truly move through time as we move through space? Join me as we delve into the science of time travel. Let's explore its possibilities, its limitations, and its potential impact on humanity. To grasp the complexities of time travel, we must first understand the fundamental nature of time itself. Time is not just a simple linear progression from past to future. It's a much more intricate and fascinating concept that intertwines with the very fabric of our universe. Imagine a vast four-dimensional fabric. This fabric represents space-time. It's a seamless blend of the three spatial dimensions and the fourth dimension, time. This fabric is the stage on which the entire universe plays out its grand drama. It's the very essence of our universe. Every star, planet, and galaxy exists within this space-time continuum. It's the canvas upon which the cosmos is painted. Three of these dimensions are familiar to us: length, width, and height. These dimensions define space. They allow us to describe the position and shape of objects in the universe. The fourth dimension, time, is a bit trickier. Unlike the spatial dimensions, time has a direction. It flows from the past, through the present, and into the future. It's the dimension through which we experience change and sequence. It's what allows us to perceive events as happening before or after one another. Now imagine this space-time fabric being warped and stretched by massive objects like stars and black holes. These celestial bodies create dents and curves in the fabric of space-time. This warping, this distortion, is what we perceive as gravity. It's the force that keeps planets in orbit around stars and governs the motion of galaxies. It affects not only how objects move through space, but also how time itself flows. The stronger the gravitational field, the slower time passes. This mind-bending concept, laid out by Albert Einstein in his theory of relativity, suggests that time is not absolute. It's not a constant ticking clock that governs the universe. Instead, time is relative. It's fluid. It can stretch and compress depending on the relative motion of observers and the gravitational forces they experience. It's dependent on an observer's relative motion and the gravitational forces acting upon them. This means that two observers, moving at different speeds or experiencing different gravitational fields, will measure different times for the same event. This profound realization has opened up new ways of thinking about the universe and our place within it. The yearning to journey through time predates our scientific understanding of it. From the earliest days of human civilization, people have been fascinated by the concept of moving through time, whether to revisit the past or glimpse into the future. This fascination is evident in the myths and legends that have been passed down through generations. Ancient myths and legends are replete with tales of time-bending feats. In many cultures, stories of gods, heroes, and mystical beings often involve elements of time manipulation. For instance, in Hindu mythology there are tales of sages who could travel through time using their spiritual powers. Similarly, in Norse mythology, the gods had the ability to foresee future events and even alter the course of history. Think of the Greek god Kronos, who controlled the flow of time. Kronos, often depicted as an old man with a long beard, was believed to govern the passage of time and was a central figure in many ancient Greek stories. His influence extended beyond mythology, shaping the way ancient Greeks understood the concept of time itself. These stories reflect our timeless fascination. They reveal a deep-seated desire to understand and perhaps even master the flow of time. This fascination is not limited to any one culture or era. It is a universal human trait that has persisted throughout history. As science progressed, so too did our concepts of time travel. The advent of scientific inquiry during the Renaissance and the subsequent development of modern physics provided new frameworks for understanding time. The invention of the telescope and the study of celestial bodies further fueled our curiosity about the nature of time and space. H.G. Wells's iconic novel, The Time Machine, published in 1895, introduced the idea of a machine capable of transporting a traveler through time. This groundbreaking work of fiction was not just a thrilling adventure story, it also posed profound questions about the nature of time and our place within it. Wells's novel challenged readers to think about the possibilities and implications of time travel in ways that had never been considered before. This groundbreaking work of science fiction ignited the imaginations of generations and sparked serious scientific inquiry. The idea of a time machine captured the public's imagination and inspired countless other works of fiction, from novels and short stories to films and television shows. It also prompted scientists and philosophers to explore the theoretical underpinnings of time travel, leading to new and exciting developments in the field of physics. Even before Einstein's groundbreaking theories, some scientists contemplated the theoretical possibility of time travel. Early physicists and mathematicians speculated about the nature of time and whether it might be possible to move through it in ways that defied conventional understanding. These early speculations laid the groundwork for later scientific advancements. But it was Einstein's work that truly revolutionized our understanding. His theories of relativity fundamentally changed the way we think about time and space, showing that they are interconnected and that time can be affected by factors such as gravity and velocity. Einstein's insights opened up new possibilities for the scientific study of time travel. It provided the theoretical framework for considering time travel as more than just a fantasy. Einstein's equations suggested that under certain conditions, such as near a black hole or at speeds approaching the speed of light, time travel might be theoretically possible. This idea has since been explored and expanded upon by physicists and cosmologists, leading to a deeper understanding of the nature of time and the potential for time travel. The human desire to transcend temporal boundaries is deeply ingrained in our collective psyche. This desire is reflected in our art, literature, and scientific endeavors. From the ancient myths of time-bending gods to the modern theories of quantum mechanics, the quest to understand and potentially conquer time continues to drive human curiosity and innovation. From ancient myths to groundbreaking works of science fiction, time travel continues to intrigue and inspire us. The stories we tell about time travel reflect our deepest hopes and fears, our longing to correct past mistakes, and our desire to glimpse the future. They challenge us to think about the nature of time and our place within it in new and profound ways. As we delve deeper into the science of time travel, we'll see how these imaginative concepts are rooted in scientific principles. The journey through time, once the stuff of legend and fiction, is now a subject of serious scientific inquiry. As we continue to explore the mysteries of the universe, who knows what discoveries await us in the realm of time travel. Albert Einstein, the quintessential genius of the 20th century, revolutionized our understanding of the cosmos. His groundbreaking work not only reshaped the field of physics, but also altered our perception of reality itself. Einstein's theories have had a profound impact on how we view the universe and our place within it. His theories of special and general relativity, published in 1905 and 1915 respectively, provided the first scientific framework for understanding time travel as a possibility. These theories were not just abstract concepts, they were backed by rigorous mathematical formulations and experimental evidence that challenged the conventional wisdom of the time. Special relativity tells us that time is not absolute, time is relative. This means that the passage of time can vary depending on the speed at which an object is moving. The faster you travel, the slower time moves for you relative to someone who is stationary. This idea was revolutionary and counterintuitive, yet it has been confirmed by numerous experiments. It slows down as an object approaches the speed of light. This phenomenon, known as time dilation, has profound implications for our understanding of time and space. Imagine traveling in a spaceship at near light speed. Time for you would pass much more slowly compared to someone on Earth. This effect has been observed in high-speed particles and even in precise atomic clocks flown on aircraft. This phenomenon, known as time dilation, has been experimentally verified. Scientists have conducted numerous experiments to test this theory, including flying atomic clocks around the world and comparing them to stationary ones. The results consistently show that the moving clocks experience less elapsed time, confirming Einstein's predictions. Imagine two synchronized clocks, one remaining stationary and the other traveling at near light speed. Upon their reunion, the clock that traveled at high speed will show less elapsed time. This difference in elapsed time, however small, demonstrates that time is not a constant, but rather a variable dependent on motion. This concept is not just theoretical, it has practical applications in technologies like GPS, which must account for time dilation to provide accurate positioning data. Upon their reunion, the clock that traveled at high speed will show less elapsed time. This difference in elapsed time, however small, demonstrates that time is not a constant, but rather a variable dependent on motion. This concept is not just theoretical, it has practical applications in technologies like GPS, which must account for time dilation to provide accurate positioning data. This difference in elapsed time, however small, demonstrates that time is not a constant, but rather a variable dependent on motion. This realization has opened up new avenues of thought and experimentation, pushing the boundaries of what we consider possible. It challenges our everyday experiences and forces us to rethink the nature of reality itself. General relativity delves into the nature of gravity. It reveals that massive objects warp the fabric of space-time. This warping, in turn, affects the flow of time. The stronger the gravitational field, the slower time passes. This is known as gravitational time dilation. For example, time moves more slowly on the surface of the Earth compared to a location far out in space where the gravitational field is weaker. It reveals that massive objects warp the fabric of space-time. This warping, in turn, affects the flow of time. The stronger the gravitational field, the slower time passes. This is known as gravitational time dilation. For example, time moves more slowly on the surface of the Earth compared to a location far out in space where the gravitational field is weaker. This warping, in turn, affects the flow of time. Time slows down in stronger gravitational fields. This phenomenon, known as gravitational time dilation, is another key to understanding the potential for time travel. It suggests that by positioning ourselves in regions of intense gravity, we could experience time at a different rate than those in weaker gravitational fields. Time slows down in stronger gravitational fields. This phenomenon, known as gravitational time dilation, is another key to understanding the potential for time travel. It suggests that by positioning ourselves in regions of intense gravity, we could experience time at a different rate than those in weaker gravitational fields. This concept has been tested in various ways, including observations of time differences between clocks on the Earth's surface and those in orbit. This phenomenon, known as gravitational time dilation, is another key to understanding the potential for time travel. Einstein's theories suggest that time travel into the future is, in principle, possible. By manipulating the principles of time dilation, we might be able to accelerate our journey into the future. This idea has captured the imagination of scientists and science fiction writers alike, inspiring countless stories and experiments. Einstein's theories suggest that time travel into the future is, in principle, possible. By manipulating the principles of time dilation, we might be able to accelerate our journey into the future. This idea has captured the imagination of scientists and science fiction writers alike, inspiring countless stories and experiments. While we are still far from achieving practical time travel, the theoretical groundwork laid by Einstein provides a tantalizing glimpse into what might one day be possible. By manipulating the principles of time dilation, we might be able to accelerate our journey into the future. This concept, while still largely theoretical, opens up exciting possibilities for the future of space travel and our understanding of the universe. As we continue to explore the cosmos and push the boundaries of science, who knows what new discoveries await us? The journey of understanding time and space is far from over, and the legacy of Einstein's genius continues to guide us.